Yes, I'm Kyrre Glette from University of Oslo, and today I'll talk a little bit about what we have done in terms of evolving morphologies and control together in Oslo. And some of the contributors to material in this talk are here in the room. That's great. So the motivation for this, let's see. Just need to get the right focus here. Yeah. So in a way you can have like there are two ways to go at this in a way. So you have biology. So you have biology-inspired robotics, or like using evolution, life to make robots. But you can also take it the other way. So use robots or use simulations to learn things about life. Often we do this type of research or evolutionary robotics. We not always aware of what we are doing. Are we doing kind of the engineering approach, taking knowledge from biology to make robots, or are we doing the opposite? Or sometimes there's a bit of both, right? I think you mentioned this earlier, Augusti, with your talk. So maybe like in this talk, I will talk a little bit from an engineering perspective, maybe. So using kind of evolutionary approaches to create robots. And the motivation for that would be that we want robots that are very adaptive when they have to go in new environments and like dangerous environments such as disaster areas. And then there's a lot of research going on to make new robot materials, like make robots that can, say, be soft, be modular, lots of different building blocks. Maybe they can even repair and make new 3D print new parts when they're out in the field. And that makes it hard to design robots when the kind of traditional engineering approaches don't apply anymore, or they are more difficult to use. So that's like why we are interested to use the evolutionary and other types of bio-inspired design approaches. So both for exploring designs to use as an, say, design tool or engineering tool, and also to adapt to environment and new situations. So the first approach, so basically there are like two sections in this talk. So the first one is about using it as a design tool. And the typical one, so I think you also had a good name for this, like in the first talk, like some using mostly simulation, and then you select a few of the results to use in hardware. So that's what we did in this approach. So do I get the pointer here? Well, that's not so important, but we do this kind of typical evolutionary robotics approach where you do make some kind of specify some kind of encoding, and you do have an evolutionary algorithm running, proposing lots of different bodies and controllers that go with them in simulation, and we evaluate them. And then at the end of the evolutionary stage, you do a physical instantiation of the selected robots that you are interested in. So here's a video showing that. It's a bit old now, but I think it kind of nicely illustrates this concept. So that this was done by Eivind Samuelsen, a PhD student in the lab previously. So you can see the robot morphology is being tested out in a simulated world. And then we had to do this process. So it was not fully automated like in the R project with a robot arm, where we had to like print out the parts and prepare them and attach servo motors and so on to test them. So with this approach, we could evolve several different solutions. So at the time when we did this, it was quite popular to do this diversity enhanced evolution by using multiple objective, where one objective is diversity of the population. So we had to specify some way of descriptions of the robots so that we could have like different robots being kind of picked by this solution. some kind of robotic distances. And then we selected 5 of those to test in the real world. We subjected them then to some testing in a motion capture setup. One problem with that was that the robot can quickly then move out of the arena, and we didn't have walls for the arena where you could actually like be sensed by the motion capture system. So instead we given a morphology, we also run an evolutionary process on how to turn using this morphology. So once you reach the boundary of the mocap area, you can apply the turning algorithm or the turning behavior to turn around and be able to measure more, because we only measured like short segments of moving forward. This had also the problem, since it's not fully autonomous, it's a tethered robot, so we needed to be able to turn in both directions, otherwise the robot would twist the cord and make failure to the system. Then we checked like real world performance, and as we heard also earlier, that like some different bodies had different reality gaps. So that was a bit of a challenge. But we could apply some type of learning on the real robot then to adjust for this. So it had some learning in the real world in this case. So in this evolutionary work, we didn't do any learning in the evolutionary process in the simulator, but we did a little bit of learning in the end. I think like if we had more computational power, we could potentially also have done learning in the simulated stage. But the controller for this type of robot is a central pattern generator based approach with some joint inputs from the joint position to the controller. So it's a little bit of a kind of robust type of control system that can easily be tuned to new morphologies. So that was one approach. And here's another approach. So this was done by Emma, who's sitting in the middle of the room here. Inspired by those, you've probably seen those videos of the gigantic strand-based kind of art pieces walking on these shores of the Netherlands, the beaches. You have this massive kind of linkage-based robots that work only by like one central rotational axis. And how you connect some rods and joints will affect like a specific way how the say one point is moving in space, and we can use that to make walking robots. So at this time we were like inspired by quality diversity algorithms and especially the map elites approach, which lets you build like a repertoire of lots of different solutions that are all of high fitness, but they're different. So that's very nice to explore a design space. And so we experimented with like say different types of mapping the characteristics of the solutions. So we wanted to see like say the length of all the rods that were used, some kind of material based characteristics and characteristics of like say the trajectory of the foot tip, and we also tested some kind of automatic behavior definitions. So these repertoires can get quite big and they're a bit overwhelming for a human designer. So we also found out that it's maybe a nice idea to make some down-sampled repertoires which capture like the essence of these ones. So that's what you see at the bottom. It's like kind of some small repertoires that present like a selection, the condensed variety of these solutions. And then we could build some of these as prototypes. So while the previous approach used 3D printing and was relatively slow, I mean, it would probably take a day also in this case to build like 3D print a robot. So when you had a Lego prototype, well, I don't know how much time you spent to build one prototype, Emma, but it was like relatively quick, right? Yeah. So it's like something in between, something that's a little bit easier to instantiate, and you can experiment a bit. And we also had this, like then you could see the robot and you could try to improve it a little bit and enhance it and so on. So that was quite nice. Here are some of the robot instantiations. So one approach walking on the floor and one walking on a carpet. So you could imagine like you have different types of terrains and maybe you don't want to take so long steps, but you want to take like a high steps instead, for example, to be able to traverse different terrains. So another approach that was done recently is the evolution of soft robot shapes. So these are actually like robots that are made of, say, small bars, 3D printed in relatively flexible materials. So in practice, they may look rigid, but in practice, they are soft. So these robots, they could be like dropped to the floor and they could still move and so on. So it's one approach to doing soft robotics. And we had this, yeah, let me try to get this pointer thing right there. So this was simulated a bit differently. So there was like a design space that was defined with nodes that could be moved a little bit around, and you could like say enable or disable connections in between them. And then like a simple simulation could be made that could calculate the forces. If you have some input force, how much is the displacement on the output node? So the theory here is that like you could have like a small displacement on the actuator, but it will give a large displacement on the foot tip. So we could simulate that also in a FEM simulation to verify that this actually worked. But the evolution was in this case run with a basic EA on this setup with like the simple fast evaluation of the displacement. But then we could do verifications, and Andrea, who did this work, he experimented a lot with different materials and approaches to this. And yeah, here's the result of one of the designs. So this one, in this case, is actuated by a solenoid, but we also wanted to experiment. We experimented a little bit with piezoelectric actuators and shape memory alloy type of things. And if you are able to like actuate fast, then you could have actually some good movements. But the challenges with these things, of course, it's the reality gap, as has been mentioned. It's also very time consuming. It's like we could only make a couple of robots of each design. So it's quite challenging to, given the reality gap, it's quite challenging to kind of do proper, like efficient evolution on physical objects. And it's also quite difficult to see the effects. Like, so in which case do you actually need one type of morphology, and when do you need the other type? So that's what the project of Tønnes Nygaard addressed. So he basically said, well, let's skip the simulations for now. I don't want to deal with this reality gap. So let's just have a real robot that can reconfigure and do all sorts of configurations. So in this case, as you can see here, there is a possibility for self-reconfiguration in hardware. So basically, we can have one physical robot platform, but it can reconfigure to several different, say, morphology instances. So it's quite limited how it can reconfigure, but it can change the length of the legs on the lower part of the leg and of the upper part of the leg. So that's a way to be able to actually do full evolution in hardware. The time to reconfigure is relatively slow, so you can't use it actively as a part of the locomotion pattern. But you can, it takes about like maybe from minimum to maximum, it takes about 1 minute. So it's possible to deal with it and test lots of different combinations. So here we do a full hardware evolution on the robot. There's of course a limitation to how many samples you can do in the real world also with this approach. But at least it was possible to do a full hardware evolution. And to save some time in the reconfiguration part, you could, in the beginning of a generation, you could sort the solutions in terms of how long legs they were using. So you could kind of do the small steps, do small reconfigurations before going to the next individual. We found that in different conditions, when you reduce the supply voltage to the robot, you can actually observe that there are different control parameters used, and there are different morphology parameters used in the robot, while at the same time achieving mostly same performance. We also tried on different surfaces, like different types of carpets, and found similar results, that there were differences in morphology parameters for these cases. But also one thing that Tønnes wanted to show was that it is actually useful to have different morphologies, because like now we could observe that different morphologies appear for different conditions, but it's maybe not given that it's better to have different morphologies and to have this adaptation instead of having just a general morphology that's an all-rounder. So that's something he showed in this paper, where he set up a robot with collecting lots of data and changing morphologies based on the terrain you encounter. And what we were able to see is that having this adaptive controller, it's the blue line, it's not that visible, will give you a low cost of transport, so like a high efficiency when new terrains are encountered, while specialized controllers are obviously not that good, and also all-round controllers are not as good as the adaptive controller. But in this case, there are, of course, challenges also. So we still don't have such a big evaluation budget. So we were doing evolution with some 100 evaluations, I think. Of course, there's wear and tear on the robot. So Lenny was talking about all these hardware annoyances, and we had lots of those, and the robot breaks down after a while. So that's, of course, a big challenge. So trying to think a little bit then about these different platforms. So they have like some different properties in a way. So some of them are very like easy, fast to simulate, like this one or this one. Like you could say, like thinking about like how long time does it take to build a Lego robot? Well, maybe it's like medium time, whereas a 3D printed robot may take more time. And in the case of the reconfigurable robot, it's rather quickly done. But of course, it comes at the cost of having a very constrained morphology variation. So there's some trade-offs here in terms of flexibility, granularity. Of course, modular robots, I haven't touched that here, but that's another, say, level, a niche of flexibility in this case. So it is like one has to consider how to get the right combination for your application. So yeah, to summarize, it's a quite challenging task to do this. There's the problem of the high sample cost. We have reality gap, and we have like problems. I think others are touching upon this topic a lot also, the encodings and how to avoid stagnation in the search and so on. And it's quite tricky to actually like see and observe that robots need to adapt their morphologies and control. That's what we tried to do, but you need really to kind of work a lot to get the constraints and the tuning right. So for now, I think that's like a key part in a way. The devil is in the details. You need to really like think about how you set up your encodings, all sorts of experiments and so on, and your environment, not least, to get this to run well. But it's also important, I think, to think about from the engineering perspective that you can use this as like a ID generator as a tool, not only as like a fully automated process. And going ahead, I think that it's quite exciting times now. There's like lots of happening on the simulation front. There's foundation models and all these kind of database things, that maybe all of this can be combined to create new interesting things. You can do so much more evaluations in parallel, that you can probably do a lot more learning and testing of different environments and so on. And we are looking at a little bit at some kind of control strategy. So like having some kind of controller that can very easily adapt to new morphologies, so we don't need to spend so much time on learning. But yeah, please feel free to come to talk to me about that in the break if you're interested. Okay, so that's it. And here's my collaborators. On the top row here is the PhD students and postdocs who did like most of the hard work. So thank you.